Okay, we'll finish up chapter 8 today, so we still have a week and a half left. Chapter 9 left in this book, so we'll finish up chapter 9 next week. It's on plane wave propagation, the coupling actually between the electric and magnetic fields, and we've kind of already seen that with the Maxwell-Faraday equation. So we've actually covered or have the correct form of Maxwell's equations, of 3 of the 4 Maxwell's equations. Actually, we've seen Maxwell's equations for the electrostatic and magnetostatic case, but there's some corrections that need to be made for the time varying case. One of those we've already seen, the Maxwell-Faraday correction. And then another one we'll see today is there's a correction to Ampere's law that due to time variation. So it's the contribution that Maxwell made to complete the set of equations that actually describe all of electromagnetic theory. So we'll look at that today, and then that'll lead us into plane wave propagation. Before we do that today, I want to take a look at generators. So last time we, as a consequence of Faraday's law, we talked about transformers. So we'll look at a very simple generator today. Have been asked to, let everyone, or ask everyone, I guess, to be careful. COVID is on a big increase here. Valparaiso went online for the rest of the semester yesterday. I think there was some discussion about us doing that possibly, but they made the decision to try and stick it out for the next 2 weeks. But that could change at any time, or actually a week and a half is all we have left before Thanksgiving break. But that decision could change at any time. I guess at most universities, there was a big uptick in COVID due to the Halloween parties. So just asked for you to try and be careful. You're also encouraged, I think, to, if you're living on campus, before you go home to visit family, that it might be a good idea to get tested. So at the Newman Center, they do testing, which is right down Walnut. I think it's free. Does anyone know? I don't know. I think you can just drive up to get tested. I have not been tested, but I don't plan on going anywhere over Thanksgiving or Christmas this year, unfortunately. But you guys will probably be going home. But it's probably a good idea to get tested before you do so, because you don't want to be responsible for getting parents or grandparents or other family members sick. Okay, so let's talk about generators. And we're only going to look at a very simple case here. So consider a single loop rotating around the z-axis. Okay, so I will attempt to draw that. X, Y, Z. And I'm going to show it initially. The loop is going to be in the XZ plane. And I'll choose this polarity for the voltage. The loop is rotating, I'll say in the increasing phi direction like that. So there's looking down from the top, it's rotating in a counterclockwise direction. And so this is what it looks like at t equals 0. Of course, to have a generator, you actually have to have some means, some mechanical means of, in this case, rotating the loop or the coil through a magnetic field. Okay, so there has to be some form of energy, mechanical energy. You know, it could be wind, it could be you know, turbine, some mechanical motor, you know, a steam engine, coal-fired, whatever, a water wheel, something to mechanical energy that is going to be turning the coil through the magnetic field to convert the mechanical energy into electrical energy. We're going to let the B field be constant in time and space. Okay, so no time variation here. For the transformer, remember that we had to have a time-varying B field in order to get the time-varying flux. Okay, here we're going to get the time-varying flux by actually rotating the loop, and we'll consider the simple case where then the magnetic field is fixed or constant. Faraday's law tells us that the induced voltage here is the negative time rate of change of the flux through the loop, or minus partial with respect to t of the magnetic flux density. So this would be the surface S. And with this polarity, you know, our contour and goes through the loop, our contour would be from the minus to the plus, which at this instant in time would put our normal in the plus y direction. Okay? With the opposite polarity, the normal to the surface would be in the minus y direction. But, so with ds is equal to n hat ds. Now, since the loop is rotating, though, n hat is time varying. Okay, it is a unit vector, so its length is always 1, but its position is always changing. At t equals 0, it's in the positive y direction, but we've got something that's rotating the loop. So our unit vector, it's always, as I've drawn it, you know, spinning on the z-axis here, it's always parallel to the xy plane. There's no z component in this unit vector, but it is time varying. Its angle is changing. So where n hat is time varying. So Vt is, I can pull out the B0 here because it's constant with respect to space and time. Integral over my surface of B hat dot n hat ds. Well, n hat here depends only on time. Okay, it doesn't depend on, it's not a function of the surface area. So this integral actually becomes just the surface area of the loop. So it doesn't actually depend on the loop shape at all. It could be a triangular, could be a rectangular loop, triangular loop, square loop, and then ddt of b hat dot n hat. Again, it's that dot product that's actually changing with time. So when the loop is, when n is aligned with b, this is 1, because they're both unit vectors. But this is constantly changing between 1, 0, minus 1, 0, 1, you know, and then taking all values in between minus 1 and 1 as the loop rotates. Or one other simplification, minus B0A. I can pull my B hat out because it's just, that's equivalent. It's just n hat that's time varying. So now I want to get an expression for n hat. I'm going to assume that the loop is rotating with constant speed, has constant rotational velocity. So now I'm going to show my xy plane, so we're looking down on this thing. And so as I've drawn it, I say what my time 0 is when n is along the y-axis. And I said it's rotating counterclockwise. So this would be, at some instant, at some time t later, and then it just continues to rotate around here. The tip of the arrow is actually on the unit circle in the xy plane because it has a unit length. I'm going to call this angle theta, where theta here, I'm saying it has constant rotational velocity, omega 0 in radians per second, or 2 pi f0, where f0 would be in hertz. So the angle here is a function of time, but this would be consistent with having constant rotational velocity. So, but using the diagram, now I can get an expression for n hat of t in Cartesian coordinates using my diagram and a little trigonometry. So n hat of t is always going to have x and y components. The x component here is actually going to be, that would be the sine of this angle. Now at time equals 0, it's in the negative x direction. So this would be sine of 2 pi f0t. Okay. The y component would actually be the cosine of this angle. And that is plus y directed. Cosine of 2 pi f0t. So, and that's consistent. If you take t equal to 0, the sine component here is 0. And then it's just y directed. But when the angle is equal to 90 degrees, here sine would be 1, this would be minus x directed, and cosine would be 0, and so on and so forth as we rotate around. Okay, so you can kind of see that that's the correct expression for that unit vector. And so the derivative of that, I'm going to factor out minus 2 pi f0. So I'm taking out the minus sign, take the derivative with respect to time of each of these trigonometric terms. I'm going to get out a 2 pi f0. The derivative of sine is cosine. Derivative of cosine is minus sine, but I pulled the minus sign out. So this would be plus sine of 2 pi f0t. And I can write this more simply as rho of t, the term in brackets, because that's just my position vector with respect to my normal. I measure phi with respect to the x-axis. So any point here in cylindrical coordinates would be x cosine of that angle and y sine of that angle. Getting this result is actually why I started the loop in that position shown in the xz plane, because it actually leads to this simplification, where this is just a time varying unit vector for rho. It would actually be at a rho hat is always at a 90-degree angle to n hat, actually. And n hat is in the y direction. When n hat at t equal to 0, though, when n hat is in the y direction, Rho hat is actually in the x direction. So rho hat actually lags n hat by 90 degrees. So plugging this into expression for VT, we get this result. V0 V hat dot rho hat of T. So when talk, so this is time varying, okay, because this dot product is time varying. Again, B is fixed. Rho hat is changing, but they are both unit vectors. Are unit vectors. So that means that dot product, it can be anywhere between -1 and 1, right? The dot product of two unit vectors is always between -1 and 1. So the absolute value of the dot product is going to be between 0 and 1. And we get then our maximum voltage would be when this dot product is equal to 1. And that is equal to 2 pi F0 A times B0. Okay. And there's some useful information there. Some of it you might be able to guess at, based on what we know about Faraday's law, that the larger the loop area, the greater the maximum voltage. So the voltage here will, if it's rotating in a loop, this will be changing sinusoidally, so our voltage would be a sinusoidal voltage. But this is just the amplitude of that sinusoidal voltage. It depends on the loop area. The larger A is, the larger this maximum voltage. It depends on the strength of the magnetic field. That's the B0 component. What may or may not be surprising or intuitive is it also depends on omega 0 or F0, the rotational rate. The faster you rotate the generator, the higher the peak voltage as well. So again, that probably makes some sense if you think about, it takes more mechanical work to rotate it at a faster rate. So you would expect greater electrical energy output. The other thing that maybe is a little surprising, maybe not, is that you'll have this maximum voltage when B hat and rho hat are aligned in the same direction. Well, remember, N is perpendicular to the surface. Rho hat would actually be parallel to my surface, then they're at a 90-degree angle. So you actually get a peak voltage when the surface of the loop is aligned with the magnetic field, which might be a little bit surprising because we know that the surface of the loop is perpendicular to the field, that's when we have maximum flux through the loop. Right? When the loop surface is aligned with the field, we actually have 0 flux through the loop at that instant. But remember, the voltage is actually related to the time rate of change of flux. So even at that instant when B and rho are aligned, we have no flux through the loop. That's when we're actually getting the maximum rate of change of flux through the loop. It's going from 0 to a positive value or 0 to a negative value. It's cross. That's when, for a sinusoid, the derivative, the peak derivative, is actually at the 0 crossings, right? At any other point, the derivative is 0. In particular, at the peaks, which would correspond to when B and rho are at 90 degrees, or when there's maximum flux through the loop, the rate of change of flux is 0. So a little bit surprising, maybe not, depending on how comfortable you are with Faraday's law, that we actually get a 0 voltage when there's maximum flux through our loop, and we get maximum voltage when there's 0 flux through our loop. But again, it's due to the rate of change of flux that generates the voltage. The other thing here, in some cases, instead of having a rotating loop, you could actually have, electromagnets or permanent magnets rotating around the loop. That would be another way to actually changing the direction of the field while keeping the loop fixed. That would be another way to generate an electrical voltage here. Okay. And the concept is equivalent. You would come up with the same result with a rotating B field here. If B be a function of time in the same manner that N is, then the result is exactly the same. In very complex generators, you might have both a moving field and a moving loop. And so both of those would contribute to generation of voltage. So the last of Maxwell's equations for the time varying case, and then I'll put them all on the table here at the end of the lecture. But for in the electrostatic case, we had this result. Which says that essentially in the electrostatic case, if we go around any loop and return to the same point, the voltage around the loop is 0. That's Kirchhoff's voltage law. Okay. Now, and it doesn't matter how small this gap is here, Faraday's law now indicates that if we've got a time varying magnetic field, so that's correct for when there's no time variation. But if we've got a time varying magnetic field or a time varying flux, as we go around this loop, we're getting a voltage here. We can make that gap arbitrarily small. So Faraday's law is correct for a time varying field. Actually says that the voltage around a loop, if there's a time varying magnetic field, again, we don't have this typically in circuits, so Kirchhoff's voltage law is valid within our circuits. But Faraday's law says that if we've got this time varying magnetic field, Kirchhoff's voltage law is really no longer valid. Okay. There is voltage generated around a loop. So the Maxwell-Faraday equation, or MFE, actually accounts for that by saying in the time varying field case, it essentially equates these two expressions for voltage. And so this is the integral form of Faraday's equation. Faraday's equation actually is this equation about voltage and time varying flux. So this one is known as the Maxwell-Faraday equation. And it is one of Maxwell's laws from Stokes' theorem. This is around a closed contour. We know that this integral on the left-hand side can also be the circulation can also be calculated by doing a surface integral of the curl of the field. So equating this, you'll see that both of these are surface integrals. And so we get del cross E is equal to minus partial with respect to T of B. Again, coupling between the B and E fields when the fields are time varying. So this is the Maxwell-Faraday equation in what's called point form or differential form. It takes place at a particular point in space, whereas an integral is an averaging over space. But it says that the change in E with position is related to the time rate of change of B. And we'll look at this a lot more actually in the last chapter, where a time varying B field can create a E field, and they can actually couple. We've got one more equation we want to look at. I think this is Maxwell's greatest achievement in tying these equations together. They were, Maxwell's equations were actually developed over a couple of hundred years, by Ampere, Gauss, Faraday. But Maxwell actually tied them all together and came up with the complete set and added this. He actually came up with this form of Maxwell's equation, but his greatest contribution was this idea of displacement current and a correction to Ampere's law. So we have this, or equivalently, in terms of current density. So, and this is Ampere's law. And this is what we've had, and this is correct for the static case. And if you recall, the picture is like this. We've got a current carrying conductor with current I, and then if we've got an H field around that current carrying conductor, associated with that, there's a contour, okay, which is on the left-hand side, and then the surface associated with that contour as well. And this is correct even when I is time varying or H is time varying. And if you recall, what we said here, S can be any surface. So you can think of it as a bubble that you can blow through, or maybe even better as the hole in a balloon where you blow up a balloon, and this is the contour, and you can blow up the balloon in any surface bounded by that hole. So now consider a capacitor with contour and surface shown. So kind of the same. Now I'm going to put a capacitor in here. And we'll have the same contour. But now I'm going to take my surface and define my surface, like a bag or a balloon. Okay, so that there's, and this was the problem. We know that there's no current flow actually through this dielectric material. So with my surface like this, with a capacitor, it appears, here if I have my surface here, I get this result. But with my surface actually going through a capacitor like this, there is no current here, and so I know that this is no longer, doesn't appear to be true, or something's wrong with my equation. Now, in the DC case or static case with a capacitor, there is no current, and the right-hand side is 0 here, and it's also 0 in the capacitor. In the time-varying case, though, I do have current here that's changing, and so in the time-varying case, I get a right-hand side here. I get current going into and out of the capacitor, but really no current through the capacitor, right? What I'm really doing is charging up one plate and discharging the other on one cycle of the sinusoid, and on the other cycle of the sinusoid, just reversing the polarity, then charging up the other plate. But here's the issue: if I take my surface like this through the capacitor, there's no current here. So this is the correction that Maxwell made to Ampere's law that made this correct. Okay. H dot dl would still have what's called conduction current. This would be the case for surface 1, and then although we don't have current flow, traditional current through our capacitor, we do have a time-varying electric flux density. Time-varying, well, the E field would also be time-varying. We have a time-varying E field in our capacitor. Now, this term, because this is current and the interval of H dot dl is current, okay, this is called displacement current. And depending on who you talk to, someone might think that that is, real current, or in my opinion, it's not a real current, and at least not in the conventional sense, because there is no charge flowing through the surface here. But the time-varying D field integrated over that surface looks like a current. And this term is necessary so that in this case, if we call this S2 and this S1, and in the S2 case, Ampere's law is correct. We can use Stokes' theorem again for the point form, and we get del cross H, and we can substitute this as del cross H and integrate over a surface. Both these are surface integrals. So you get del cross H is equal to the current density, conduction current density, plus the partial derivative with respect to T. This is displacement current density. And so this is the more general form of Ampere's law. Sometimes it's called Ampere's law with Maxwell's correction. And this is the part Maxwell added to make all these equations consistent. And so in Maxwell's equations is kind of the peak of everything we know about electromagnetism, okay, and everything kind of the pinnacle of electrical engineering. Everyone who graduates with an electrical engineering degree always looks back on this course as the hardest course they take in the undergraduate curriculum. Certainly the hardest, probably theoretical course. So, and it's dealing with Maxwell's equations, curls, divergence, all of that stuff. But we finally got there to Maxwell's equations. And it takes a long time using Maxwell's equations and working a lot of problems with before you actually get really comfortable with them. But here they are. We've encountered them all at this point. This is called Gauss's law. Okay. It was one of the very first equations that we looked at, one of Maxwell's equations very early in the course. And then the second one is Maxwell-Faraday equation. There's an integral here, b dot ds. Or in point form, it's del cross E is equal to the minus partial derivative of B. And this is the Maxwell-Faraday equation. And for most of this course, we were working with static electric and magnetic fields. And so this partial derivative with respect to time was 0. And so this actually on the left-hand side that led to Kirchhoff's voltage law. So if there, but in the time variation case, you know, this is no longer 0. Instead, we get a voltage generated due to the time varying flux. The divergence of the magnetic field is 0, and that's true for static and time varying fields. This is Gauss's law for magnetism. And the final one of Maxwell's equations is Ampere's law or del cross H is in point form plus the partial derivative of the D field. So this is Ampere's law with Maxwell's correction. So the homework problems for this are actually fairly simple. I think in one case, you're given one of the problems you're given the D field and asked to find, it's as a function of time and asked to find the displacement current density. Okay, so don't confuse the displacement current, though, which is the integral of a density over a surface area, with a displacement current density. The displacement current density is just simply the time derivative of the D field, and it exists at a point. All right, that is it for today. So just one more week to go. Try and hang in there. We're almost through this semester.